Hello dear ladies and gentlemen, my name is Shahrukh Ababov and we're the Drillbotics team of the TUC Laustal. We'll start off our presentation with a small introduction of our team. We're the student team here consisting of 5 people. I said my name is Shahrukh Ababov. Other members by the name of Nikolai Tambotsev, Charalampos Solemetsidis, Lila Koro and Philip Klassen. We would really like to thank our advisors and supervisors. Advisors by the name of Master of Sciences Wolfgang Holstein, Master of Sciences Ramaz Abdallah, and the supervisors Professor Dr. Philip Jäger and Master of Sciences Eric Feldman. So, started with a small introduction of the team. Next point, we'll go through the setup of our drilling rig. We will discuss the hardware components that are built on the rig, the software that's running behind all the hardware components and bringing them all to function. And then we'll talk about the implementation and integration of the software and interaction of software and hardware components. We'll close off our presentation with the lessons learned and the small summary of our experience in this project in the last 6 months. Our end goal is to learn and apply the learned knowledge in practice and be able to pass that learned knowledge to the next team in the coming years. Our drilling setup consists of 6 main components. First, we'll discuss the drilling string. The drilling string is powered by an electric top drive at the top of the rig. The electric top drive propels an flexible shaft which runs in a static drill pipe, with the help of which we're able to apply the needed weight on bit pressure at the bottom hole. The rig was designed for low torque, high RPM grinding. The next part, or the next module of our rig is the drilling fluid circulation system. This system consists of a 2-stage pump system. The first pump is a pre-charge pump, followed by a high pressure pump, which is able to generate up to 120 bar pressure. At the bottom of the rig, we have a rock sample receiver, in which we place our rock sample, and on the sides of the rock sample receiver we have 2 coils with the help of which we generate our own magnetic field, which is then supposed to help us orientate us in the stone and correct the azimuth. The next module is the steering system. We have a 3-pad push-the-bit steering system, which is actuated by 3 independently working hydraulic surge units. The next important module is a rotary table, which is driven by an asynchronous stepper motor, and it helps us to enable azimuth corrections. Last but not least, we have the Z-axis. It is driven by an electric motor over a spindle, and it helps us generate the needed weight on bit pressure and move the hoisting system. You can see here the complete setup of the rig. It consists of this aluminium traverse, the Z-axis with the spindle, the top drive unit, which is located here, the syringe unit, as you can see here at the top of the rig. The drilling motor is located here. Our BHA is here, as you can see, in the rock sample holder. And the high pressure pumps are behind the whole system, so they're not able, it's not possible to view them. And here's the rock sample receiver, as I've already noted. Here you can see our BHA with the steering pads. These have been developed by the previous teams. We tried to hold ourselves to the original design And here down the picture you see the actual model of the BHA. We've developed a custom drill bit, which, as I mentioned before, our machine is designed for high RPM and low torque grinding. So you can see here that the drill bit is pretty smooth. It's been diamond coated, and on the BHA you can see the sensor units. That's our IMU. We have an accelerometer here, which helps us measure the inclination, and a magnetometer, which helps us orientate with the help of the azimuth. And this part of the BHA, the string gauge, is visible. This enables us to read the real-time values of the weight on bit in the bottom hole. On this page you see our syringe unit system. There are 3 syringes in total. Each syringe consists of a stepper motor, which rotates a screw. It's a superfine screw which moves here. Actually, when it's turned, it moves and basically increases pressure in the hydraulic lines, which is then applied on the pistons, which are located in the BHA. The pistons then move and actuate the steering pads, which help our BHA navigate in the bottom hole. As I've mentioned, the syringe unit consists of 3 syringes, 1 syringe per steering pad, and each syringe is actuated separately. So thank you very much for listening. On this page I will hand it over to Philip Klassen, and he will continue with the main software components.
Thank you, Mr. Bobov. I'm Philip Klassen, and I'll introduce you to the software components and the algorithm. Here we have the main software components, which divides in 4 parts. All our modules are based on Arduino. Our control algorithm are based on Python and are running on a Raspberry Pi. Our architecture is based on the Django web app, which is written in Python, and our GUI is based on Java. Now I'm going to explain you our 3 main control algorithm. I'm starting with the initialization algorithm. We started the algorithm if we are put our main switch on, and then we can choose if we want to start the script or not. If no, we are going back to our default setup. If yes, we start to send messages to our modules and waiting on an answer. And if we are going, some modules don't answer us, we're going back to our default setup. If all are there and answering us, we're going further and write our parameters on our module, so we get the right units and measurements from them, and our output is ready. Then we can take some user inputs. If no, we are just waiting, or the algorithm is waiting until we're doing something. If we are set some inputs, the relays goes on, and we are homing the z-axis and rotary table. The magnetometer and accelerometer are taken on 0, and it finds the azimuth of the BHA. And the hook load and the weight on bit are took on 0 too. Then it finds the rock 0, so the rock surface, and it goes on a sanity check if the weight on bits and the hook load are plausible. If no, we are going back to the default setup. If yes, we are going further to the park position on the z-axis. Now I'm explaining our drilling algorithm. We start with the user input. If we take an input, the relays goes on and starts the pre-charge pump and the high pressure pump, and then we watch if we have a flow. If no, we are going back to our default state. If yes, we go further and our motor starts to rotate. Then we watch if we get our needed RPM. If no, again, we're going back again to our default state. If yes, we go further and set our weight on bit and read again the mission date. If the data is okay, we're going further and watch if we have a survey station. If not, we are drilling further. If yes, we execute our survey station. And now I'm coming to our survey station algorithm. If we reach a survey station, we stop drilling, the RPM set on 0, and we drive back on the Z-axis for 5 millimeters. Then we are waiting until the drilling hole is cleaned by the mud and apply again the weight on bit. Then we measure the angle. Then we drive again back on the Z-axis for 5 millimeters and restart our motor unit and apply again weight on bit and drilling further. Now I hand out to Mr. Solomesides. He's gonna go through the steering algorithm.
So thank you very much, Mr. Klassen. And yeah, I'm gonna go through the steering algorithm. At first, we're gonna separate the algorithm into two parts. We have the on one side the well path interpolation, and on the other side the path force algorithm. So yeah, first we have to interpolate a well path, which is doable with our drill. So with a high enough curvature radius to make it possible to reach. Yeah, and the next part will be then the path force algorithm, where we go a little bit into detail how we calculate the forces for each pad. So what is happening here in detail? We have as an input for our function 4 points: the start point, the kickoff point, our first and our second target. We enter them into our function and also enter the amount of service stations that we want to do on our well path. The function then gives us our trajectory. It gives us the trajectory in coordinates. So we get a lot of points that we can use as our target points that we have to hit. How is that established? We divide our trajectory into equally large spaced drilling segments, and between those segments we have our service stations. And these service stations also are used for us as our targets that we want to hit. So let's assume we start our drilling process. We are currently in the 0, 0, 0 position, and then our first target would be our first service station that is calculated out of the interpolated path. Yeah. So when that has happened, we assume we hit our service stations. We are at the predicted point. But how did we manage to apply the forces required for steering? This is going to be presented in the next slide. Right, there we are at the next slide. How is this established? So at the start, it's a little bit of an easier solution, since the BHA plane and our coordinate system, so the coordinate system in the BHA plane and the coordinate system of our whole system are the same. We can just project our target point onto the XY axis, and then calculating the direction vector. And if we turn the direction vector by 180 degrees, we will get our force vector, which then has to be divided into two components which are in line with the pads. So this is not always possible, because if we hit our first target, we will already have a inclination and an azimuth in our bottom hole assembly. And if we imagine now that we are slightly deviated from our previous path and have a slight inclination, the coordinate system of the BHA and our whole system are not the same anymore. So what we have to do, we calculate our BHA vector, the vector that points in the same direction as our BHA, out of azimuth and the inclination. and create a perpendicular plane to this vector. So, and if we have this plane, we can project the target point onto the BHA plane and then do the same thing as I explained already in the previous state. We calculate the direction vector, turn it by 180 degrees to get our force vector, and then use Lami's law to calculate each pet forces. So, and let's just assume we have our target point spaced in the somewhere between C and A. Let's say like in the picture here, which is mentioned, which is shown here. Let's say here's our target point. We projected it onto our plane, and now we have to turn it by 180 degrees. So if we do this, we get our force required for steering, the sum of the force, and now we have to divide this force in a component for pet B and a component for pet C. So if we do this, we can divide B and C with each other to get the relation from those both, because we are not drilling with we are not going to use the calculated force. We will say that we power one pet by 100% and the other pet by the relation of it. So here it could look like, yeah, we are powering pet B with 100% and pet C with like 35% of the power of the whole power. Yeah. Also, the third pet, the one of three pets is not activated, so it's going to be set to 0, and then these pet forces are going to be constant until we reach another service station when where the whole calculation is going to be done again. So now Mr. Klassend and I mentioned already a lot of different algorithms, and also Mr. Abrorov mentioned a lot of different modules existing on our rig, and the question comes up, how is this managed? So we have a lot of different modules that are wanting to communicate with us. How did we establish a communication with all modules, and also how did we establish to let the modules communicate with each other? Yeah, we decided to implement a CAN bus network into our rig, which makes it possible for us to send messages into our CAN, and also to send the messages in such a way that only the desired module receives it. So we just assigned different addresses to all modules, and if we send a message with for example the address of the syringe unit into the CAN bus, only the syringe unit will read out the message and do whatever it whatever the message says that has to be done. So this only works with messages that we are sending in, but also with the modules with each other. So, for example, the z-axis could send a message with the address for the wait on bit and ask, and ask for the current wait on bit. Yeah, the wait on bit unit will receive the message and then send out the current wait on bit to the z-axis. So not directly to the z-axis, it will send it on the CAN bus. We will also receive it, but the z-axis will also read out the message and then pursue whatever the z-axis is wanting to do. Right. This for the CAN bus setup. On this picture, there are just some modules implemented. There are a lot of more modules which we will see in the next slide. I'm going to go not too much into detail, but I'm just going to show you some examples of the big architecture. We also included the big structure plan of our rig into our report, and we tried to stay as close as possible to the plan, and yeah, just gonna go to the next slide. Right, so here's our big structure plan where we can see our different supply lines, our CAN bus network, also our drilling mud lines, and different parts that are setting different modules into relation with each other. So I think the most crucial part is right here where we have our power plug and we come into the switch cabinet. Here we have first of all our main switch and different circuit breakers for safety purposes, and then we come to our 5-volt supply line which powers all CAN modules. So from here on we can send a message to the relay module and tell the relay module to turn on whichever relay we want. As we can see, relay 2 and relay 3 are assigned to the pumps in our system, so the pre-charge pump and the high pressure pump, and right, also there is the fourth relay for the coils. Mr. Abrov mentioned that we implemented our own magnetic field, which makes it a little bit easier to measure correct azimuth for us, because the Earth magnetic field is like a little bit weak, but this we can see over here. Right, the CAN bus architecture was one part, but as we can assume, there is going to be a lot of data coming into the CAN. So we had to come up with an idea how to store the data and or make it available, and also make it visualized in a graphical user interface. So when a lot of data comes through, something has to read in all the data, sort it, and give it out into a readable format. Yeah. So for that reason, we implemented a dynamic data architecture, and I'm going to go through it in the next slide. As you can see here, this is a quite simplified version. We have here our CAN network and our data handler, which is reading all the messages in and sending it in a frequency to the Redis layer. So what we can think of the Redis layer, we can imagine it as an virtual storage space. And it stores data in the RAM, so it's very fast, and yeah. The Redis layer then passes the data over to the consumer to the second Redis layer channel, which then hands it over to the GUI. So in the consumer we have our functions that can be also called by the data handler, and right. Also, the consumer can read in data coming from the GUI. So if we imagine that we press a button in the GUI will send it to the Redis layer, and the consumer is listening here. If there's data, the consumer is taking the data and passes it over to the commander, and the commander is able to pass it back to the Redis layer and then back to the data handler and into the CAN, right? So this is our small structure to make our data visible and usable. And this is it for my part. I will hand over to Mrs. Koro, which is gonna go through the GUI. And yeah, thank you very much.
Thank you, Charalampos, for handing over to me. Last but not least, we can see here our graphical user interface. It enables us to see some important data in real time over a web browser. As you can see here, we can view the parameter like RPM, when weight on the bit, and orientation of the PHA in the borehole, as well the rate of penetration. So to close off the presentation, we summarize the experience that we gathered during the building and designing process. some major points that have to be noted for the next team. For example, having more than one plan is crucial. Having alternative when working with companies could be beneficial, and also focus on just one platform to collect all files and document. Thank you for your attention, and see you on Monday.